Lifshitz.
Okay, well, yeah, thank you for the introduction. I'm Elena Corbae. I'm a graduate student in the Actions group at Stanford. And yeah, I'll be talking about the superconducting gap and Hund's coupling influence across the Lifshitz transition of the hole-overdoped barium, potassium, iron, arsenic that we've been hearing a lot about. First I just want to acknowledge all of our collaborators, many of whom are here today. Also I want to give also a special a special mention to Dr. Donghui Liu and Dr. Makoto Hashimoto, who are the beamline scientists at SSRL, where all the ARPES spectrum that are shown are taken at beamline 5.2, and they make the measurement very nice there, so lots of thanks to them. I guess I'll introduce this 122 family. I've been hearing a lot about this, so maybe I'll not spend too long, but basically we have this parent compound, barium, iron, arsenic. This has a filling of N equals 6, and then you can substitute potassium on the barium sites to push to N equals 5.5 filling, where again for these d orbitals, half filling would be N equals 5. So we expect correlations to increase as we hole-dope it. And also, so this is a figure of the crystal field splitting for an iron 2+ in a arsenic tetrahedron environment. And you see that, the active orbitals that we expect are these, I don't know what to do, XY, XZ, YZ. This is phase diagram, and we see that superconductivity emerges from a magnetically ordered ground state, which shows kind of striking similarity to the cuprates, but we see that there's kind of this strong anisotropy between the electron doped and the hole doped side, where for the electron doped, as you dope away, superconductivity eventually goes away with electron doping, whereas for hole doping, stays superconducting for all these potassium hole doping levels. And here, optimal doping is at around 40% potassium with the TC of 38 Kelvin. So I'll introduce some of the fermiology now. So there's notably 3 hole pockets around gamma. The innermost are XZ, YZ, and XY is the outermost. Around the, also I'll say this now, I'll be using the terminology of the zone corner is M. So technically in this tetragonal gluon zone, it should be X as the zone corner, but for consistency with the other iron families, I'll be using the convention that this zone corner is M. But there's 2 electron pockets around this zone corner, the outermost being DXY and the innermost being XZYZ. And this is just a figure of some of the LDA for, I think, just like a generic iron system, so this isn't for the barium 122 specifically, but it's reflected here, again, the 3 hole pockets. And then, as you hole dope it and bring down the Fermi level, you eventually go through this Lifshitz transition where you should, in theory, lose this XZ electron pocket as the YZ starts to cross the Fermi level. So then you're replaced, these electron pockets with this idea that you have now only hole pockets around the zone corner, which look like these petal-like pockets. And so, having lost the ideal fermiology where you're, instead of scattering from hole to electron, you're now in theory scattering from hole to hole. And you can ask, is there a change of superconducting pairing symmetry across the Lifshitz transition? It's widely accepted for optimal doping that there's this spin fluctuation induced isotropic S+- pairing where you're scattering from the hole pockets around gamma to the electron pockets around M, with this sign change happening between those 2. And then on the fully potassium dope side, there's one ARPA study on this now where they claim that there's nodal S+- with only hole bands. So some things to note on this is they have this nodal behavior on the middle Fermi surface sheet, and they have this gamma band is 0 everywhere, which this has XY character. And yeah, they say it's nodal in the pockets around M as well. So yeah, so we see that we have this non-ideal nesting fermiology, but robust and kind of exotic superconductivity. And then that puts us in the regime that we've been talking about, this broken time reversal symmetry. So these are inelastic neutron scattering studies, and on the electron dope side, they basically see that with increased electron doping and increased mismatch of the hole and electron pockets, your spin resonance scales with TC and eventually goes away. However, on the hole dope side, it's similar to the electron dope side in that the resonance decreases with this increasing mismatch of the hole and electron Fermi surfaces, but we know that it stays superconducting for all these hole doping levels. And something else that I guess is a bit interesting is this single scattering Q vector splits into 2 incommensurate peaks with hole doping. So something to note. So yeah, this asymmetry between the electron and hole dope side, we can ask why does superconductivity survive with hole doping. So in addition to kind of that open question, we've heard a lot about this very rich multiband phenomenon, where we have the broken time reversal symmetry and these fractional vortices, both of which I think the current theory relies on this idea that it's multi-component. So then to get a better understanding of that, we can try, or attempt to get a better understanding of that, I should say. We can use RPES, which is kind of able to directly probe these different bands. So yeah, with that in mind, we perform RPES studies of 3 superconducting hole doping levels, one of 41%, which is right around optimal doping, one of 53%, which is above optimal doping but below the Lifshitz transition, and one of 78%, which is above the Lifshitz transition and technically in this broken time reversal symmetry regime. And then we have one normal state measurement of the fully potassium doped, because yeah, we can't go below the superconducting level for that. So yeah, first these are the Fermi surfaces, just showing one of the M pockets, but there's C4 symmetry, so it's all around. So we confirmed that the Lifshitz transition occurs between 53 and 78% doping. So again, notably, you can see that these kind of log-like electron pockets around M become petal-like there. So yeah, confirm the Lifshitz transition happens. And then using different experimental geometries, we can do some orbital assignment, and we confirm that the innermost are XZ-YZ character, and the outermost being the DXY bands, and then yeah, this DXY electron pocket and DXZ-YZ, which becomes YZ-XY. And yeah, something I can point out. So yeah, these are the dots here are the experimentally fit bands, and then overlaid with the DFT, which I'll talk more about later. But yeah, you can see at 78%, I have this dotted line here. So I'll talk more about this later, but we see that the YZ band crosses the Fermi level. So we expect the XZ pocket to not be there anymore, but we still have some signatures of it. So I'll talk about that a bit more later. So yeah, now we can look at superconductivity around gamma. So the top row is these gamma to M cuts, and the second row is gamma to X cuts, and these are the 3 different superconducting three different hole doping levels, and yeah, these are symmetrized spectra, and the green line indicates where the cut is taken for the YZ band, and the blue line indicates where the cut is taken for the XY band. And so what we see is that we can resolve a gap on this XY band at 41%, that closes above TC, as expected, but when we increase to 53%, which is still below the Lifshitz transition, we can no longer resolve a gap on that band, which is a bit surprising because maybe we expect the same bands to participate in pairing below the Lifshitz transition. Whereas for the YZ bands, we're able to see a gap on all 3 hole doping levels that stays open. So yeah, just in conclusion, here's around 41%. We have these basically isotropic gaps that are consistent with other literature on the system. The smallest being in this gamma DXY band. When we go to 53%, we begin to see more anisotropy in the gamma, or from the gamma to M to gamma to X direction on this beta band. And again, the XY band, the XY gap is closed everywhere around the Fermi surface. And for 78%, we see that, yeah, we still have this anisotropy between the 2 bands. However, if you remember, the fully potassium doped study said that it was nodal for this beta band, which we don't see. We still resolve a gap. Yeah, with that, we can maybe claim that the nodes that they see are accidental, or if they're symmetry enforced, maybe there could be some lifting of the nodes from broken time reversal symmetry. Could be one reason. Now we can look at superconductivity around M. So the top row is in an experimental geometry to kind of best see the DXY band, so this one here. The second row, we look for the XE pocket, and what we see is that we actually can resolve a gap on the XY band, which I think previous literature has been not so clear about being able to see both band gaps for both electron pockets. So I think, yeah, we see 2 gaps on the XY and XE. But we actually see that the XY pocket around M kind of mirrors what we saw around gamma, where the gap disappears by 53%, and yeah, stays closed for 78%, whereas the XE pocket stays open for all these doping levels. And again, this 78% doping is where we don't necessarily expect this pocket to be, but we do see a gap open on this band and closes above TC. So yeah, this is also kind of a summary of the variation of the superconducting gap in the gamma to M direction. And what we see is that the circles are around gamma and the triangles are around M. We see very similar values both around gamma and M for the XZ and YZ band, whereas a much smaller gap on the XY band, both around gamma and M. So we see this very orbital dependent anisotropic gap sizes. So that is, yeah, a bit interesting. Now talk about the shallow pocket around M a bit more. So yeah, by C4 symmetry, if the DYZ band crosses EF, then BXZ should be above F, above EF, which is yeah shown here. Yeah, we confirm that we see the YZ crossing, still it's XZ, and this has also been seen at a higher doping level in another study, and they described it as a resolution tail. So we can ask, is it a resolution tail or could there be some broken order? So something to know with this is we're only fitting the YZ band kind of around here. We're not actually fitting the very band top, so there might be, it might be more flat or some momentum dependence. But this is kind of our best attempt at this for now. But we see that, yeah, not claiming that there's any broken order here, but maybe this is within some error bar, this gap between the band top and band bottom. But it's much bigger for the 78%, or maybe I shouldn't say much bigger, it's bigger for 78%. So this is still kind of an unresolved question for us, of whether this is some broken order or, yeah, if it's just some trivial thing. But I think it is interesting that this occurs in the vicinity of so many other instabilities that we've seen and have been talked about. So yeah, something to keep in mind. But then again, yeah, this gap opening here is this 3-band model that yeah, Vadim and Igor have been talking about that might fit this broken time reversal symmetry picture. So yeah, this is just a bit of a summary for these superconducting measurements for now. Where again we go from these isotropic gaps to more anisotropy, isotropic being within the own bands, and then yeah, again from this final study, I see it's nodal over here. Yeah, so now we can talk about some of the normal state. So I think as the last speaker talked about, there's these orbital selective correlations in iron-based superconductors due to this Hund's coupling. So showed this figure earlier, but yeah, once you have this crystal field splitting that lifts the degeneracy of these bands, then you kind of have this competition of how to fill the no longer degenerate bands. And Hund's coupling comes in, which is basically the energy scale associated with intra-atomic exchange. So I save JH by placing electrons in different orbitals in a high spin configuration as opposed to in the same orbital. So this can act as a different origin for strong correlation. And notably, I think one of the big consequences of this is it acts as a band decoupler. So it blocks these interorbital fluctuations, so you can't gain in delocalization energy for J greater than 0 by hopping orbitals. And so what that means is that these bands can have very different correlation effects based on the individual filling. So I think, yeah, this figure here shows these 3 degenerate bands that get lifted by crystal field, and then the narrower of them then is pushed closer to this half filling and closer to this orbital selective Mott phase. And then when you keep on increasing U, then you can end up in a true Mott insulator state. Yeah, but there's this concept of this orbital selective Mott phase. So that was theoretical, but there's really nice evidence of this Hund's coupling experimentally. So this is from a review where it basically finds that the stronger the overall correlation, the stronger the orbital selectivity in the dxy orbital. So yeah, these are different iron families, and yeah, with increased dyz renormalization, there's also an increase in the ratio of dxy and dyz. And then this is also an RPES study which shows an orbital differentiated coherence-incoherence crossover in this 1-1-1 system. And yeah, again, they see this reduction of the spectral weight specifically in the dxy orbital as you increase temperature as opposed to the dxz and dyz bands. So yeah, back to our study. So our collaborators do DFT that takes into account the changing lattice structure to account for screening as well as this increased doping. And yeah, when we compare that to our experimentally determined bands, we see a clear trend of an increase in the renormalization for the dxy band specifically as you increase hole doping. So that is something we see as one piece of evidence for this increase of the Hund's coupling. We also do temperature-dependent studies and see that there's basically, as a function of temperature, we see that as we increase doping, the dxy band is, yeah, selectively lowered, lowers the spectral weight, and yeah, as we increase doping, even at the same temperature, there's kind of a difference in the coherence level. As you can see here, it gets this dxy peak gets broader and broader at 40 Kelvin, and then also the dotted line is 100 Kelvin, and it's kind of no longer resolvable at 78% doping. On top of that, we also see this spectral weight redistribution where not only does the XY band get less coherent, we actually see that the YZ band becomes sharper and has this increase in spectral weight. So yeah, you can see that these green bands are the YZ here, and yeah, they get sharper as you increase doping. And yeah, that's also reflected in these MDC cuts around the Fermi level where, yeah, this outermost being the XY, this peak being YZ, and yeah, you see if you increase doping, this shift in these ratios of them. So yeah, now we've seen two proxies for increased Hund's coupling influence with doping. So we saw these orbital-dependent correlations and orbital-dependent coherence-incoherence, all for the DXY band specifically. So now we can ask, is there any connection between the superconducting normal state? I'll try and make some kind of naive arguments. So taking the Q vector from the neutron scattering paper we saw before, we can overlay that on the experimentally determined Fermi surfaces, and what we see is also it's a fairly, I mean, take this with a grain of salt. The Q vector is fairly broad, but when we overlay that, we see that there is kind of fairly good nesting between the XZ, YZ hole pockets and the electron pockets, but that's true for both the XZ and XY electron pockets. Whereas for the outermost XY hole band here, it's very poorly connected to any of these electron pockets around N. So yeah, what we see is the superconducting gap size for DXY, if you remember, is very similar around gamma and M, although the two pockets have very different scattering properties. So we can maybe try and rule out any type of like interorbital pairing, but maybe we can ask what is the, like, why do we see this gap on the DXY band at all? Maybe there's some interorbital pair hopping. I don't know, maybe the theorists can comment on that more. But I just, yeah, want to make a point. And then for 53%, one of the arguments made in the fully potassium doped paper was that the reason why the XY band is 0 around gamma is that it's close to the S plus minus boundary. But we see that around 53% where the gap is 0, it's like not that significantly close to the S plus minus boundary, and it's not too different than 41%. So yeah, but all this being said, it kind of begs the question of what's so different for the XY orbital here. And so it can ask, yeah, does the fermiology play a secondary role for the superconductivity of the DXY orbital? And so if that's the case, what could be the reason? And so this is one paper where they try to account for this orbital selective superconductivity by addressing these Green's functions with the quasi-particle spectral weight included. And so this top is the susceptibility. Without dressing in the bottom is the dress susceptibility. This is specifically for an iron selenide model, I think, and take it with a grain of salt because, yeah, I think that there's some question about the gap structure that they determined for that paper. But the idea is there that including the spectral weight contribution suppresses contributions from orbitals with small weight factors. And they basically need to have these dress spin fluctuations necessary to reproduce the experimental gap structure that they determine. Yeah, but the idea being, yeah, suppression of pair scattering due to the reduction of quasi-particle weight. Next, this paper goes kind of a step beyond just the quasi-particle spectral weight by including the dynamical effects, DMFT. And what they find is that the increased Hund's influence leads to spectral weight redistribution and an energy window JH around the Fermi level. So yeah, for low Hund's coupling, they have some characteristic DXY around the Fermi level and DXZ, DYZ, whereas when you increase this Hund's coupling, the DXY is suppressed and actually the XZYZ is increased. And so with that, they do this superconductivity model, which I think that they're only considering intraorbital pairing, but they see that this increased Hund's coupling leads to large orbital differentiation in superconducting gap size and also superconductivity that persists for more parameters here. So low Hund's coupling, higher Hund's coupling. And so, yeah, we see from these papers that Hund's coupling may help to explain the anisotropic gap and persistence of superconductivity with hole doping. So this, I think someone else will be talking about this paper specifically later, so I won't say too much about it. But you can ask, what about further hole doping? And so they chromium dope cesium-122 to try and push past that 5.5 filling towards true half filling. And what they see is these very large Sommerfeld coefficients, which I think are the largest of any iron family. And then they start to see the signatures of the onset of magnetism. So yeah, we see that we saw from our own studies that the DXY band is becoming more localized with increased hole doping. They see with further hole doping it's becoming or this system is becoming more, but they're seeing these very large Sommerfeld coefficients. And so, yeah, that leads to the question, which turns out this is a 2014 paper. I thought that I arrived here on my own conclusion, but maybe everyone has had this idea for a while. But you can ask what's the true paired state of the iron superconductors, because we're used to thinking about it from, this n=6 filling, but yeah, perhaps this Mott insulator is the true paired state, and then you get superconductivity from that. So yeah, that leads to kind of this picture I have, where again, you have this different parent state perspective, and then in that case, superconductivity, is emerging from this localized phase, which is much more similar to cuprates as you dope away. Maybe these very localized dxy electrons are acting as kind of the the background of the itinerant carriers of the XYZ orbitals. Now we also revisit this picture where we have we see that Hund's couple, or we see it becomes Hund's metal for these higher doping levels, and you can see the dxy effective mass increase there as well. So we can ask if the increased influence of Hund's coupling may explain the observed orbital dependent superconducting gaps. These are the conclusions, reflections. We see increased influence of Hund's coupling with increased hole doping. We saw this trend of increased renormalization for the dxy band, an orbital differentiated coherence incoherent spectral or crossover and spectral wave redistribution. We saw a very anisotropic superconducting gap structure, which might not just be explained by a simple S plus minus nesting picture. And we can ask, does Hund's coupling also help explain the persistence of superconductivity with hole doping? Thank you.
Ilya, yes.